Welcome to Easy Math TV. This is part two in our two-parter on constructing a confidence interval for the difference between two proportions. And we're going to answer a question here. The claim is that the proportion of men who use tobacco is not the same as the proportion of women who use tobacco. So essentially, we had this big sample. And if you look at these two sizes, the two sample sizes, I want you to imagine that it's all one big sample. And we have 420 plus 560 people that were surveyed. So that's a total of 980 people that were surveyed in this big sample. And we're splitting it into two populations by a certain attribute. And that attribute is men versus women, okay? So in column C, if you remember from our first video, part one was already recorded. So basically, if you missed out on how to create all this data here in column C, you'll want to stop this video now and go back and review part one first and then come back to this, okay? Because we've already seen how all of these numbers were entered and how they were calculated. So it even tells us in the problem there were 980 adults who were randomly sampled. Of those 980, 420 were women and the rest were men, okay? So the rest was this 560 that you see up here in E4. We also had, in the sample, that is, 10% of the women used tobacco compared with 15% in the men. So certainly there is an appearance of a difference between the two, right? It looks like 10% is different from 15%. But the question is, can that difference just be explained by random chance, or is that a true difference between the two groups statistically? So we're going to look and see whether that perceived difference has any statistical significance to it, okay? We've already discussed how to calculate these things here as well. We had our test thresholds calculated, and then we calculated this quantity here called the standard error. And when we're dealing with the difference between two proportions, what's important for everyone to understand is that there are two different versions of standard error. One of them is for the confidence interval calculation. The other one is for a hypothesis test. And it's really important that we actually use the right one. So it's hard to tell that there's even a difference between these two here. And part of the reason for that is that our sample was just so large. We had a really decent size sample, and so it's hard to tell the difference between those two standard errors. But as a general rule, it's important that you use the right one. Okay, so this formula used our p-hats in the calculation. Um, the the actual sample proportions were used in calculating our standard error for the confidence interval. Okay, and we had to take the square root of the sum of two fractions. So these two fractions that you see here, C5 times C6 divided by C4, plus then E5 times E6 divided by E4, those are the two variances that are attributed to the two samples, okay? And then you take the square root of that. To do the standard error for a hypothesis test requires something called a pooled proportion, okay? I'm not sure if we really want to get into that right now, but since we're on the subject and since we do have it on our spreadsheet, let's just go over the pooled proportion. The pooled proportion is a weighted average between the two sample proportions. So the first sample proportion was 10%, the other one was 15%. So we do expect the pooled proportion to be somewhere in between those. But it's going to be weighted because one of the sample sizes is significantly larger than the other one. Okay, so because there were a lot more men that were in our sample, then the 15% is actually going to uh, bear more weight than the 10%. So we calculate the pooled proportion by adding our two sample successes, x. So that's going to be our 84 plus our 42 in parentheses. So equals parentheses C3 plus E3, close parenthesis, divided by the total of our two samples. So, I mean, we could have just put a 980 there, but since we want to be able to use this spreadsheet again and again, we're going to use cell references there so that we can just alter the data at the top and just be able to use all of this for ourselves. So the pooled proportion is equals parenthesis C3 plus E3, close parenthesis, divided by parenthesis C4 plus E4, close parenthesis. And if you wanted to grab a calculator and see what that is, notice that's 12.857%. If we were to just kind of figure that out on a calculator, look at our two x's. Our two x's are 84 plus 42. That's, let's see, let's calculate that out. So that's 126. And our total of the two pieces of the sample, the total was 980. So if I divide that by 980, then multiply by 100 to get a percent, it's 12.857. See that? 12.857. And there we have that in our spreadsheet. 12.857. That is our pooled proportion. And then we also need to subtract that from 1, and we'll save this standard error for the hypothesis test for the next video when we're actually doing a hypothesis test, okay? But let's hold off on that. So let's go over here and talk about our confidence interval itself. How is that built? So it's built by using the difference between our p-hats as our point estimate of the true difference. So remember, the question we're asking here is, what is the true difference between these two populations and their tobacco use? So we want to be able to capture the true difference between this lower limit and upper limit here. So in order to do that, we start with what we call a point estimate, which is our P1 hat minus P2 hat. So that should be at the center of our confidence interval. So P1 hat just happens to be 10%, which is 0.10. So if we basically just subtract that, so 0.10 minus our 15%, which is 0.15, and multiply by 100 to get a percent. So that's negative 5%. A difference of minus 5%, which means that the proportion of women is actually smaller than the proportion of men, because we subtracted them in that order. We subtracted the women minus the men. So we got a negative number, which means that at least in our sample, the P1 hat was smaller than P2 hat. And that negative 5 should end up being exactly in the middle between our upper limit and lower limit that you see in purple here, okay? If you were to actually put those three numbers there on a number line and be very precise about it and careful, the minus 5 should be exactly in the middle between negative 9.89 and negative 0.11, and it actually is. Okay. So how did we calculate the lower limit and the upper limit for our confidence interval? Well, lower limit is equals parentheses, so we start with our P1 hat minus P2 hat, which is C5 minus E5, and I put that in parentheses so that you could actually separate that out and see that that is our point estimate in the middle. And then minus our margin of error. And the margin of error is the standard error for a confidence interval, which is E9, times our z-score that we calculated in the first video, which is in cell C12. Okay? So again, so putting that all together, it's equals parenthesis C5 minus E5, close parenthesis, minus C12 times E9. And that's your lower limit. The upper limit starts again with equals parentheses C5 minus E5. So you'll notice the first part is exactly the same. But instead of subtracting C12 times E9, we're going to add C12 times E9. So plus C12 times E9. Again, that's equals parenthesis C5 minus E5, close parenthesis, plus C12 times E9. And hit enter. So the question comes down to, is the number 0 contained inside the interval? Because if 0 is contained in the interval, then you would have to say that there is a possibility that the true proportions might actually be the same, because then when you subtract them, you get 0. So if yes, then any perceived difference could be due to random chance. The two populations could still be the same despite what the samples suggest. If no, so basically if these two numbers are both the same sign, they're both negative or both positive, then 0 is not inside that interval, and that's what we have here. Then the difference between the two samples is in fact statistically significant. So there is sufficient evidence to show that the two populations are in fact different. So how would we state that in our conclusion over here? Our conclusion would be, and again, our confidence level was 98%. So we had put that up here in cell C9. So with 98% confidence, women do in fact use tobacco between, and I rounded the percentages to 9.9% and then 0.1%. So women use tobacco between 9.9% and 0.1% less, and the less is because they're both negative, okay? Less than men. We have verified the claim, that means, because the claim is that they are in fact different. So we have proven that, all right? And that's how you construct a confidence interval for the true population difference between two proportions when you have sample data to look at, all right? Like, subscribe, comment down below. Next time we will go over the hypothesis test, and you know, a lot of our conclusions are going to look very much the same, but the way that we approach it is a little different, okay? See you in the next video.